Well, good morning or good afternoon, depending on where you are. Thank you, everyone, for joining us today. Here's the flow of what we will cover. I will give you guys a high-level overview of this release of AIM, and Steve will jump on and talk about some of the technical details of this release, and we will finish up with Tejas showing the demonstration of some of those key elements that we put into the release. So first of all, I want to kind of step back and not necessarily assume that all of you on the line have used AIM extensively and are deeply familiar with it, but give you an overview of what AIM does, what it's all about, and what are some of the value propositions of AIM. And just for your benefit, personally, I come from a CAD background. I'm very CAD heavy. I was a design engineer. So the market that AIM is after, design engineers, is someone like myself, and so I can appreciate the journey that people are going through as they're learning AIM and finding out what it's all about. You see all the pictures on the screen, and it gives you an idea, and this is not meant to be something comprehensive, but it gives you an idea of the breadth of physics that AIM is all about and what it's letting engineers solve. Okay, so you can see in the middle there 3D engineering simulation with a broad breadth of ANSYS physics in one user environment, one single user environment. So that's really what AIM's about, that focuses the design engineer and on multiple types of physics. If you want to go to the next slide, Steve, let's talk about some of what I call the value propositions are. What makes AIM very different? Okay, the first one up there, an unmatched ease of use with guided workflows. Again, me personally, coming from a design and CAD background, I really appreciate in AIM, if I want to set up a structural or an FSI study, I'm guided through all the steps that I need. There's defaults that are set up. There's suggestions that AIM gives me. And I was able to pick this software up very, very quickly. Really, it took me about a day to figure out the flow. And, okay, I get this. I can set up my own fluid study or structure study. It really wasn't difficult at all. Behind the scenes with AIM, this is not a different set of solvers. This is not a low-end offering by any means that ANSYS is giving to its base, but you have the same proven solver technology behind AIM that you have with the flagship products. Okay, so that makes a big difference. And just for your benefit, as I have talked with customers, as I have talked to many people, I've learned this is a big reason that people appreciate AIM. They're finding with maybe other simulation tools, the accuracy just isn't there, and they're getting poor results. They're testing, they're matching up the results from a simulation tool to test results, and it's just not there. When they try AIM, and the results are much, much better. Okay. We talked about the broad capabilities, this third point, of all the applications that AIM covers. So you don't have to get necessarily separate individual packages, but you have everything right there. You have exposure to any kind of, not any, but your major fluids simulations that you want to do, heat transfer, fluid structure interaction, electrical applications, structures, you name it. And with that, you have the option as a design engineer to say, I want to stay in silos. I want to use just multiple physics. For this particular application, I just care about structures. But maybe for another one or something related, you care about a fluid structure interaction. So you have that option to tie together physics or keep them separate. Customization is a great one. If you look at those guided templates on the right-hand side, you as a user or someone as a methods group manager is able to set up some kind of a template and guide your users through the options that you want them to change or set in stone, other parameters in your company that you don't want to change. Okay, and then finally, collaboration. So AIM is a great tool to use as a preprocessor. What we mean by that is setting up your geometry the way you want it and mesh in AIM and passing that information to someone else that might be using ANSYS Fluent, CFX, mechanical to do more higher fidelity study and run simulations on that level. So information can be passed back and forth via Workbench, and so information that or simulations that you run as a designer are not lost, and a more dedicated analyst has to start over. That's very much not the case. So that makes, all those things make AIM very different, very unique. I like to think of it as a heck of a lot of power in one package that's very accessible for your what I'll call the average design engineer. So one more slide to go through just to kind of set the stage for what this release is about and how it fits into the scheme. If you take a look at all the way on the left-hand side, release 16.0 a few years ago. This was really the introductory release of AIM, where the major capabilities, what I'll call the fundamental or essential capabilities of physics, were there. Every release from there, we have added important, crucial things that designers need. So you see 16.1, UX improvements, 16.2, conjugate heat transfer, something very important. And then we started adding some electronics capabilities, magnetostatics, sorry about that. And finally, when you get to 18.0, what I think of as the major physics are there. Now we are rounding out the corners and adding these niche things that are very important to many people still, but we're putting things in that may not be as popular to the masses, but many people are still going to be able to benefit. Solver-dependent expressions, displaying multiple results at a time. That's something that everybody can really benefit from, and Tejas is going to show. So I'm very excited about this release. I think it's great. I'm a little bit newer to the scene with AIM, but as I have spent some time using it, I just really appreciate all the work that has gone into making this product the way it is, and especially this release too. I'm going to turn things over to Steve now, and he's going to walk you through some of the technical details of this release, and then we'll go over to Tejas to show a demonstration of important capabilities.
All right. Thanks, John. All right, so as John said, I'm going to spend a little bit of time and go over some of the highlights of AIM 18.0. And as with every release, we've made enhancements in fluids, structures, and electromagnetics, as well as a number of general enhancements. I'm going to hit the highlights of some of the features in each of the major physics disciplines and also talk about some of the general enhancements. This is not an all-encompassing list of all of the new capabilities that are in AIM 18.0. With each release, we put about 40 to 50 new features into the software. So I'm just going to hit the highlights, but there are a number of other new features that are detailed in some of the update materials that are available on the customer portal. Okay, so with that, let's dive right into the details. And I'm going to start out talking about the fluids enhancements. And the first enhancement is solution-dependent expressions. And this is a very powerful capability that allows you to include field variables, so things like the velocity or the mass flow, and quality functions, so being able to take the average velocity or the minimum pressure or the maximum mass flow, and take those field variables and quality functions and include them in an expression to define boundary conditions. This is a very powerful capability, limited really only by your imagination. But the example that's shown here on the slide is one possible application of a solution-dependent expression, the ability to represent a manufacturer's fan curve using an expression. So the example we're looking at on the slide is a fan-cooled fuse box where we've taken the outlet mass flow and computed the CFM at the outlet, and then used an expression to represent the fan curve and applied that fan pressure at the inlet. So this is just one way that solution-dependent expressions can be used to define boundary conditions. Again, a very powerful capability, allows you a lot of flexibility in defining fluid boundary conditions. The next capability that I'd like to highlight in fluids is the ability to take model information from AIM to Fluent. So what this allows you to do is to take advantage of the pre-processing capabilities of AIM, allowing you to prepare the geometry the way you'd like to using the integrated modeling tools, generate a mesh, and then transfer the part or volume mesh and the selection sets to Fluent to do a more advanced simulation. This is available via the Workbench project schematic. It's also available via a new AIM template. But if you're a designer, and let's say you've calculated the pressure drop through that valve, what it allows you to do is pass that model setup information to an analyst in your company to maybe do a more advanced simulation. Maybe you're interested in looking at the effects of multi-phase flow or cavitation. So from an analysis of a pressure drop through the valve, you could then pass that information into Fluent for an analyst to do a more advanced simulation, taking into account more advanced physics options. Okay. Also in the area of fluids is the enhancement to do one-way fluid structure interaction with shell structures. So, I mean, we have the ability to take fluid forces and solid temperatures from a fluid simulation to a structural analysis. In 18.0, this has been extended to also support shell structures. So if you're modeling structures that are relatively thin and you want to take advantage of modeling the structure with shell elements, you now can take fluid forces from a flow simulation and map those to a shell structure to take advantage of modeling a structure using shell elements. So there's a new option for physics coupling to take fluid forces for structures like this dish antenna, where you're mapping the fluid forces to a shell structure. There's a new gap tolerance, which is based on the shell thickness, and there's also the options for manual controls. Okay, shifting gears a little bit, we'll hit some of the highlights for structural analysis. Continuing with the theme of expressions for boundary conditions, there's some new capabilities in structures for expressing boundary conditions using expressions. So the two new enhancements at 18.0 are the ability to use an expression to represent a spatially varying force and a spatially varying pressure. So if we look at the example shown on the slide, we have a tank with a hydrostatic pressure load. So the pressure is a function of the depth of the fluid inside of the tank. So what I can do to make the setup of that easy is just set up a couple of variables, one for the density and another for the gravity, and then write a very simple expression where I'm representing the pressure as a function of the density of the water, the gravity, and the position. And the expression can reference the global coordinate system or a user-specified reference frame such that we're using the appropriate Z position. But just another way to make it a little bit easier to deal with complicated loads, extending the expression support for structural forces and spatially varying pressures. Okay. Also, in the area of structures is another new capability for boundary conditions, the ability to use a cylindrical reference frame for displacement and support conditions. So what this does is it allows for a more flexible specification of cylindrical constraints. So let's say we want to apply a pin joint to those cylindrical surfaces of this cover. There's a number of different ways to do this in AIM, but the new way to do this at 18.0 is to use a cylindrical reference frame for the support condition. With a cylindrical reference frame for the support condition, now I have the flexibility to constrain the radial, axial, and tangential directions on those cylindrical surfaces versus just constraining the X, Y, or Z direction. So it allows for more flexible specification of cylindrical constraints, useful if you're modeling things like shafts or other rotating components. As I said, there's a number of different ways to do this. I could use a joint to represent that pin joint, but this is a new capability allowing a more flexible specification of boundary conditions for either a displacement or support condition. Okay. And also in the area of structures, another enhancement is in the area of bolt pretension. So this is a new option for bolt pretension where a single bolt pretension can represent a collection of bolts. So if you're working with a bolted connection where you have a lot of bolts, might have been a little bit tedious before 18.0 to set up a pretension bolt for each one of the bolts around this series of bolts in the bolted connection. Now by using a single bolt pretension, you can just pick all of the bolts at once and then specify that you want one bolt per location or one bolt for all locations. So it just makes it easier to set up bolted connections when you're working with a lot of bolts. There's some new options for post-processing bolt pretension results as well. It's now available in the AIM post processor. It's the ability to post process the bolt adjustment as well as the bolt working load. So the bolt working load, this represents the force reaction from the pretension load. So this allows you to see what the force is in the bolt after you've applied all of the other structural loads and boundary conditions to the model. So again, just some ease of use enhancements and some post-processing enhancements to make it a little bit easier and more straightforward to work with a bolted connection. Okay, and then finally, switching into the third major physics area, which is electromagnetics. Before 18.0, we had magnetostatics in AIM, as John mentioned. New at 18.0 is the ability to look at magnetic frequency response. So if you're working with a device that is driven by an AC current, and you're interested in eddy or displacement currents, you can now solve magnetic frequency response problems using AIM. The magnetics template has been enhanced, so you can see there's a new option in the magnetics template for frequency response. So this gives you a guided workflow for looking at the magnetic frequency response of a device. You also have the option to include frequency-dependent materials. So something like this glass crucible induction heating problem, we have a series of copper coils which are running with an alternating current, and that's generating eddy currents in the liquid glass. So we can solve this problem now in AIM 18.0 using a magnetic frequency response and solving for the eddy currents in the liquid glass. Another new enhancement in the area of electromagnetics is, again, an enhancement to the magnetics template, is the ability to automatically create the surrounding region. So let's say I was interested in looking at a magnetostatic analysis of this relay geometry. I might have this geometry in my CAD system, and I want to do a magnetic analysis. Well, I could certainly create the enclosure in my CAD system or use the integrated modeling tools in AIM to create an enclosure, but this just makes it a little bit easier. So right on the magnetics template, I can check the box to create the surrounding region, just import my CAD geometry, and AIM will automatically create an enclosure to represent the surrounding air or vacuum domain around my electromagnetic model. So it just makes it a little bit easier to set up a magnetic problem by automatically creating the enclosure around your CAD geometry. Okay, and the third enhancement that I want to highlight in the area of electromagnetics is one-way magnetic thermal coupling. Now, in AIM, we've had one-way coupling between DC electric conduction and thermal analysis. We've also had one-way coupling between magnetostatics and steady-state and transient thermal. But now at 18.0, we've included one-way magnetic thermal coupling between magnetic frequency response and either a steady-state or a transient thermal simulation. So going back to the glass crucible heating, this is an induction heating problem. So not only are we interested in the electromagnetic solution, but we're interested in how much heat we're generating in that liquid glass. So now you have the ability to do one-way coupling, where you can use a physics coupling region or physics coupling interface to couple the electromagnetic solution, specifying the frequency of the source, and then specifying where you want those losses from the electromagnetic solution applied to the thermal model that are going to generate heat. So this allows you to take the total loss from a magnetic frequency response to either a steady state or transient thermal simulation to calculate the temperatures that are a result of those losses from the electromagnetic solution. Okay, and then the last sequence of slides I want to share with you before we move into the demonstration is some of the general enhancements in AIM 18.0. The first one is in the area of post-processing, and this is pretty straightforward. It's just allowing you now to display multiple results in the same display. So in the AIM post processor, the group view now allows the display of multiple results. So when you bring up the group view, basically you can just turn on or off individual results, and the groups of results will be displayed on the same display. So if we look at an example like this two-cycle engine where we've solved conjugate heat transfer, we can display the velocity vectors, a calculated value, and a temperature contour on the same display. So displaying multiple results allows you to create more impactful graphics where you can combine vectors, multiple contours, calculated values, all on the same display. This can also be combined with the realistic material rendering to create very impactful images and animations to allow you to effectively communicate your simulation results to your colleagues and customers. Okay, this is another new enhancement, another new general enhancement, and this has actually been pretty commonly requested, the ability to modify the background color of the AIM user interface. So at 18.0, we've allowed fairly basic control, but what it allows you to do is allows you to change the background color to either a light, white, or a dark color theme. So this is available under the workbench options, and this can also be changed on the fly. So if you start AIM with the light theme and you decide you would rather use white or dark, it can be changed right while you're in the session. So you can see the difference. Again, just personal preference, whether you want to use the default light theme, which is a light gray background, a white theme, which actually happens to be my personal preference, but you can pick from white, light, or dark, which again, just depending on your user preference. Okay, and then I also wanted to highlight that we've introduced another regional language option for AIM at 18.0. AIM is currently available with an English language version. AIM's also available with a Japanese language version. We've introduced a third language at 18.0, which is a Chinese user interface. So this can be set, again, under the workbench options. So under Tools Options, Regional and Language Options, you can set a Chinese UI for AIM. Here you can see an example of some of the menus with the Chinese translation of the AIM user interface. The obvious benefit is that this provides a local language version for native Chinese speakers. Okay, and then the final slide that I want to go through before handing off to Tejas for the demo is I just want to talk about some licensing changes at 18.0. AIM, as you know, is available as a standalone product, and AIM has also been available with our multi-physics bundles. So the mechanical CFD product, the mechanical CFD Maxwell 3D, and the mechanical EMAG Maxwell 3D products. So AIM was available with the multi-physics bundles and also as a standalone product. Now at 18.0, AIM is also included with the new Mechanical Enterprise and CFD Enterprise licenses. So if you are an enterprise customer, either a CFD Enterprise customer or a Mechanical Enterprise customer, AIM is now included as part of those product bundles. So this gives you access to AIM either through the integrated enterprise license or through the component prep, post, and solver licenses. And this is true for both mechanical CFD and mechanical enterprise. It's a shared license in both cases, but if you're an enterprise customer, you now have access to AIM. You could try out some of the pre-processing functionality. If you're a CFD user and maybe you have to do some structural requirements that you need to do, this now provides you some structural capabilities in your CFD license. And conversely, if you're a mechanical user, you need to do some CFD or maybe some electromagnetics, you now have some CFD and electromagnetic capabilities in your mechanical enterprise license. So this is a new bundling of AIM with the enterprise licenses, but for all of you enterprise customers, you now have access to AIM in either the mechanical or the CFD enterprise license. Okay, so with that, I will turn over the presentation to Tejas, who will show us some of the new features and a live demonstration.
Okay, thank you everybody for attending. Thank you, John and Steve. What I'd like to do is illustrate AIM through a couple of examples. These are already solved examples because we don't have much time to solve in real time. But I think this should give you a very good idea, number one, of what AIM is all about. And it also highlights along the way some of the new features in version 18. So for this demo, you can see on my screen I have AIM open, and I'm using the new light background or white background selection, in case you're curious. You can see here I have kind of a pipe with a butterfly valve in the middle, and you can see it has a large inlet on top and a smaller inlet on the right-hand side. And in this application, we're going to assume that you have a hot fluid coming in from the small inlet on the side, a cold fluid coming in from the top, and you have some sort of mixing going on depending on the angle of the butterfly valve as well as the location of the inlet. So the engineering goal for this example is to understand the mixing of the hot and cold streams and understand the impact of that mixing on the temperature distribution on the pipe which is downstream of the valve. So ultimately we want to look at the temperature distribution of the solid, so we're doing a conjugate heat transfer problem, and that is one design goal. The second design goal is to do a structural simulation where we don't care about flow forces or anything like that, but we want to do a bolt pretension type analysis. You can see these bolts holding this assembly together, and then apply a load on top here, pressing it down, and try to identify where your stress hotspots might be. Now, typically, to do the simulation, you might have to open up a CFD tool to do the conjugate heat transfer, and then once you're done with that, go into another tool for structural analysis. What AIM allows you to do is do all these analysis in a single user interface, which you can see in front of you. So the simulation process templates that my colleagues John and Steve mentioned are all listed over here. And the simulation process templates that I used were the fluid solid heat transfer template, and you can see that's the first workflow on the bottom. And then I independently used a structural template to populate the workflow on the bottom over here. So let's take a look at some of the details of each individual step. As has been mentioned before, AIM guides you through each step of the workflow. So here I have my geometry step. You can see that I have the valve angle parameterized and is available for me to make parametric changes if I want. Under the mesh task, you can see here that I have a mesh which has been created for conjugate heat transfer. So it is very appropriate for a CFD style solution. So if I show the solid body and the fluid body, you'll see with just a couple of small controls, I'm able to automatically create a mesh which is very, very high quality. You can see I have, of course, inflation or boundary layers around all the walls. I have a hex mesh in the bolts. I have automatic curvature-based refinement of these curved areas. And I also have proximity refinement, which automatically ensures that there's a minimum of 2 elements in the thickness of the solid part. So this mesh is very nice, very refined, but the time it took for me to set up this mesh is literally 30 seconds. All I've done is turn on curvature and proximity global sizing function, and then I applied a body sizing to the fluid domain. And also another thing I want to point out is meshing in AIM is physics sensitive. So you'll notice under the engineering intent, it knows that this mesh is intended for fluid flow or conjugate heat transfer simulation. So it automatically adjusts the default settings to give you a mesh that is already highly optimized for this application. And then all you have to do is a couple of small refinements to get what you want. So with many CAD embedded simulation tools, this kind of mesh is very, very difficult to accomplish with such less effort. Okay, so here we have the mesh, and you can see it's very nice. And this took me about a minute or 2 minutes to create. Okay, if you go into the flow task, you'll notice that the panel here guides you through all the main settings, specifying the different physics regions, material properties, boundary conditions, inlets and outlets, solid thermal conditions in terms of insulated boundaries, convection. All of those are very easily assigned using the GUI name. Okay, and then more importantly, of course, are the results. So if I look at the results, you can see here I'm plotting the multiple results simultaneously. This is one of the features that we talked about. So here I'm looking at the outlet temperature value. I'm looking at a streamline colored by temperature, and I'm also looking at the temperature of the solid downstream of the butterfly valve. So here you can see that the flow is coming in straight. The butterfly valve is at a 0 or wide open angle, and all of this looks good. But because of the mixing, you have this temperature gradient on the wall. Now, you as an engineer can decide whether this is appropriate or not, and you can make changes as you see fit, right? Now, once I've done with this simulation, which you can see highlighted in the workflow panel on the bottom, I can use the same geometry, and I can jump into a structural simulation. And the great thing here is I've not jumped into a different user interface. I'm using exactly the same user interface, exactly the same style of mesh, same panel and same inputs for creating a mesh. The only difference is in this case, the mesh has been fine-tuned automatically for structural simulation. So since we're using a finite element style solver, it's automatically using the appropriate element types and so on to solve this kind of problem from a structural perspective. So we think that this makes AIM a very nice platform for bringing simulation early upfront into the design process, because any engineer can learn how to use this very quickly and just learn a single tool to be able to do multiple types of simulation. Okay, so now let's just look at the setup for the structural solution. Once again, you can see it's very similar to the setup for flow simulation. The only difference is the inputs are structural in nature. So we have fixed supports, we have a force, we have bolt pretension, which is something that's newly improved in version 18. We have specified contact, and you can see, we can use standard bonded contact, or we can use the full range of nonlinear contact that's available in our fully featured ANSYS mechanical tool. In this case, I've also done a multi-step simulation. So in the first step, we have activated the bolt and locked it, and in the second step, we have turned on the force. So all of this is standard in AIM. And when we look at the results, you can see this is the first step. So you can see the stresses due to the bolt pretension being applied. And then if I go in here to my second step, you can see the stresses as a result of this top face being forced down and identify where your hotspots are going to be. So in this example, I've done a baseline simulation of this valve geometry. We have done a standalone CFD simulation where we're displaying temperature and flow solution. And then in the same user interface, I've done a standalone stress analysis where I'm displaying stress due to bolt pretension as well as stress due to a load applied on this flat surface. Okay, so now you might say, well, I've done my initial analysis. Now I actually want to change the design. Now you could change the design by clicking this replace geometry button and importing a new geometry from your CAD tool. And by the way, AIM is completely CAD agnostic. So you can use any CAD system of your choice and directly import models in that native CAD format. That's no problem. However, I want to point out that AIM also comes built in with our own direct modeling solution. So if I just click edit geometry, it pops me into our native geometry editing tool, which is based on SpaceClaim direct modeling technology. And I can start doing things like this. So for example, I can say, I want to change the location or orientation of this inlet piece right here. You can see that I can directly change this without having to mess around with a history-based solution. So with just a couple of clicks, I have taken this model and I have changed the angle of this of the inlet pipe. I can similarly go in and you can see here that I have a value, a parameter value for the valve angle, and I can change this to whatever I want, right? So with just a couple of clicks, I have made a change to the geometry, and now if I exit the geometry editing phase, you'll see that my model in AIM is updated. And if you look at the workflow panel at the bottom, you'll notice that all my inputs from the first simulation are preserved, and all I have to do is right-click on results and click update. And it will apply the same mesh settings as before, the same solver settings as before, and it will even preserve all my post-processing so that I can quickly visualize the results for this new configuration, and compare it to the baseline case. So hopefully you saw how easy that was to change. Now I'm not going to make you wait through a solve. I already have a solved case, and here's that solved case. And if we look at the flow results for this solved case, you'll see that the temperature profile on the straight pipe is very, very different now, which is kind of obvious because the flow is going up this way. And now as a result, we have a very, very different flow distribution. And this may be good, this may be bad, but it allows you to very quickly evaluate the impact of these kind of design changes. It allows you to make that design change very quickly, but it also allows you to study the impact of the design changes in a highly automated way. Okay. Now, you'll notice down at the workflow level, I actually have a much more sophisticated workflow than before. Not only have I done resolved the fluid flow case, which is my first simulation process, I have resolved the structural simulation. The same thing. We're looking at the bolt pretension. We're looking at the first step and the second step. This solution doesn't change a whole lot because the design changes really didn't impact the structural integrity. But in addition to that, I'm actually doing a one-way fluid structure interaction by mapping the results from my flow simulation, which you can see highlighted at the bottom, to a FSI for force. So now what I'm doing here is I'm using what we call physics coupling to apply the flow forces on this valve from the flow simulation to a stress simulation, right? And if I look at the results over here, I'm able to predict the deformation. Of course, this is an exaggerated deformation. I'm able to predict the stresses and deformation of this valve due to the flow forces, okay? Then I can go even further and I can say, well, I want to do another fluid structure interaction, but in this scenario, I'm going to do a physics coupling, but the physics coupling is going to take the solid heat temperature, the solid temperature predicted by my flow simulation, and I'm going to map that to my structural simulation, and I'm going to take a look at my thermal stresses as a result of those non-uniform temperature gradients and identify where those hotspots are going to be, okay? So I hope you see the power of doing all of this in a single user interface with a very, very easy to use GUI and having access to all these different physics in one place and having all these physics talk to each other and share a common geometry module, share common mesh settings, share very common physics settings. So like was mentioned by John, AIM is so easy to learn and so easy to use that all our training is just online based on YouTube videos and documentation available at our customer portal. And from my experience, any engineer, even if that engineer has never done simulation in his or her life, can get up and running with doing this type of simulation in less than a day, just using those tutorials that are available online. And that is truly powerful. So I think with AIM, we have really given very powerful simulation to the hands of any design engineer so that they can take advantage of simulation upfront and improve their product as much as possible before sending it off to the analyst for final verification or before sending it out to prototyping and testing. And that's it for my quick demo.
All right, thanks, Tejas. And we're going to show you one more thing real quick before we jump to questions and answers. I just wanted to highlight, again, some of the new capabilities and show a third physics in AIM, which is electromagnetics. And this is a solenoid valve example. So, looking at the butterfly valve that Tejas just showed, it is another design consideration might be the solenoid control that controls the valve. So here we have a workflow, and you can see it's a very similar workflow to what Tejas just showed for fluids and structures, where I have a geometry. Again, I've used a template to automatically set up an enclosure, and I'll just hide that to make this assembly a little bit easier to see. Simple solenoid valve configuration where we have a plunger and a coil, an outer case, and we're going to specify a DC current in the coil that's going to create a force on the plunger. So I'll just quickly run through the physics setup. For electromagnetics, the electromagnetic solver uses adaptive meshing. So what you'll notice is the workflow is a little bit different in that there's no mesh task. So you go right from geometry to setting up the physics, and the meshing is taken care of as part of the solution, where the solution will automatically refine the mesh to meet a specified convergence criteria. I'll just quickly review the setup and we'll show you some results. The outer enclosure volume is air, so that is defined by the template. I have some steel components, which you can see highlighted here. So these are all components which have a nonlinear magnetic permeability. So I've specified a BH curve as part of the steel 1010 material assignment to account for the effects of material saturation. We have a polyethylene insulator around the coil, and the coil, which is made out of copper, is inside that polyethylene insulator. And then we also have a stainless steel sleeve that the plunger slides up and down inside of, and the stainless steel component is also not a magnetic material. So we have the material properties set up for the model. And I'll just also highlight the electromagnetic conditions, which are pretty simple. What is going to generate the force in the plunger is a coil. So a terminal and a winding define the coil. So this coil happens to have 1,000 turns, and the current is half an amp. So the total number of amp turns for this coil is 500 amp turns, and this will generate the magnetic field and generate the force in the plunger. Again, I'm not going to run the solution live. This runs pretty quickly. I'll just quickly show you the solution convergence plot. And what you can see is this blue line shows the increase in the mesh density. These orange lines down here on the bottom show you the convergence of the error energy in the magnetics mesh. So again, the adaptive meshing is automatically refining the mesh with each solution pass to meet the target accuracy. And again, we'll just take a quick look at some of the results. I've predefined some of the results already. The most important result that we're interested in is the force on that plunger. So you can see for this position of the plunger, we're generating about 7.8 newtons of force on the plunger. We might be interested in some of the other electromagnetic results as well. So for instance, we might want to take a look at the current density in the coil. And as we expect, we see a nice uniform current density in the coil. And then we also might be interested in looking at the magnetic flux density in the steel 1010 components. So that can be displayed as a vector quantity. Can also be displayed as a contour. And you can see we're getting a little bit of material saturation in those corners. But again, just a real quick overview of the workflow for electromagnetics. As you can see, the setup for the materials, the boundary conditions, the results post-processing, virtually identical to structurals and fluids. So what this allows you to do is easily branch out and explore other physics disciplines. So you're not limited by just structures or fluids. Any design challenge that comes your way, you're able to tackle with the multiple physics capabilities that are included as part of AIM.